Okay, let's just dive right in. Imagine a world, maybe not even that far off, being built like right now, where hundreds, maybe thousands of AI agents don't just, do tasks. They actually live together.
Right?
They form societies, they take on roles, they work together, and build something that starts looking less like code running and more like, well, a civilization.
It's a pretty mind-bending idea, yeah.
Welcome to the deep dive. Today, we're digging into some really cutting-edge research that's tackling exactly this. It's this technical report, and it's laying out the groundwork for, well, potentially creating these huge AI agent simulations. They're focused on the basic steps needed to build what they call AI civilizations. So for this deep dive, our mission is, I think, pretty clear. We need to unpack the why and the what. Why are researchers even trying to build AI societies? What's the problem here that current AI just can't handle? And what are the sort of core, maybe brain-inspired ideas behind the solution they're proposing? We're going to try and take these big concepts and, break them down so we can all really get what this new frontier in AI is about.
That's exactly it. Because you see individual AI agents doing some pretty amazing things already, right?
Yeah.
Writing code, browsing the web, playing really complex games.
Yeah, impressive stuff.
But this research is looking ahead and asking that really tough question. What happens when you go beyond one agent or just a few and try to get hundreds, even thousands, working together? How do you get that complex emergent behavior when you scale things up like that? That's the massive technical challenge this paper is trying to figure out.
Okay, so let's start with that big vision then, the why. Why pour all this effort into building, an AI civilization? What's the real motivation?
Well, the paper makes this really strong argument right at the start. They basically say that for AI agents to truly become part of human society, to coexist with us in meaningful ways, they can't just be tools we point and click. They need to be autonomous, sure, acting on their own. But, and this is key, they also fundamentally have to be collaborative. Living with humans means understanding social stuff, working on shared goals, contributing to things bigger than just themselves.
Okay, so moving past the idea of just a lone AI genius to AI being like a social player.
Exactly. And they actually use that word civilization, which is pretty bold, but we should be clear, they define it very specifically for their research.
Right, it's not like tiny AI empires or something.
No. When they talk about an AI civilization, they mean an advanced society of agents showing high institutional development. So that includes agents taking on specialized roles, maybe some kind of organized governance emerging, and collective progress in areas we associate with human progress, science, art, commerce, but all within their simulated world.
Got it. So it's about the structure and the collective results that can happen when lots of these agents interact dynamically, not robot history reenactments.
Precisely. And they make this pretty big claim that measuring this civilizational progress, how well these agents coexist, self-organize, make progress in systems that look like human ones, that's maybe the ultimate benchmark for AI agent ability.
Wow, okay.
It totally shifts the focus. It's not just, can this AI write code? Or can it win this game? It's, can it function and contribute effectively inside a complex, evolving artificial society?
That really does move the goalposts for evaluating AI. It's asking if an agent can thrive within a system, not just at a task. So why should you, listening right now, care about this vision of AI civilizations? What's the takeaway?
Well, it matters, a lot.
Yeah.
Because it's really about the building blocks for how AI gets integrated into our world in the future. If AI is going to be more than just, a command line helper or a chatbot, if it's going to be a genuine collaborator, maybe even a peer in some situations, we have to understand how these complex systems, made of potentially thousands of these autonomous AI things, actually behaves. This research is step one in understanding that complexity. It pushes AI beyond just isolated tasks into this realm of complex, emergent social stuff, organizational behavior. It's laying groundwork for artificial entities that could eventually interact with our world in really deep systemic ways, not just one-on-one.
That makes a ton of sense. It's about getting a handle on AI as a collective force, not just individual units. Okay, so that's the big why. Now let's shift to the what. What's the current state of play? What do AI agents and these multi-agent systems actually look like now based on the paper, and where are the gaps this research is trying to fill?
Right. So as most people know, modern AI agents are often built around these powerful large language models, LLMs.
Yep.
And these agents usually have this kind of modular setup. They use different LLM-powered bits for different thinking jobs. So you've got modules for reasoning, figuring things out, modules for memory, remembering stuff, modules for planning, figuring out steps to reach a goal, and modules for using tools interacting with the outside world, like searching the web or using a calculator.
And these single agents are already doing some pretty cool things on their own.
Oh, absolutely. They're being used all over, writing code, automating web tasks, being really sophisticated players in games, lots of applications.
Okay, so individual agents are getting pretty smart. What about systems where you have multiple agents trying to work together? Is there research on that already?
Yes, definitely. There's a whole field looking at multi-agent systems,
Okay.
and the paper goes through it. They kind of group the existing research into areas like productivity, games, and social modeling.
Okay.
So in productivity, you see multi-agent systems used for things like software development. Maybe different agents handle coding, debugging, testing, working together.
Uh-huh.
They're also used for coordinating teams of robots, automating science experiments, or even simulating complex things like negotiations or debates.
So agents collaborating on a specific, usually pretty well-defined group task.
Exactly. Often with a clear goal everyone shares and a pretty structured setup. Then there's research using game environments. Games are great test beds for studying how agents interact in simulated worlds.
Right, like agents playing multiplayer games against each other or maybe working together on quests.
Yeah, that kind of thing. And the third big area is social modeling. Here, multi-agent systems are used to simulate complex human or societal stuff.
Like what?
Oh, things like modeling how kids learn socially by watching agent interactions, simulating game theory outcomes, building economic models, testing social policies, studying how communities or social networks evolve.
Wow, okay, that covers a lot. So we've got smart individual agents and systems where multiple agents interact, simulate social stuff, or work on specific goals. So where does this paper say the big limitations are, especially when you want to build something on the scale and complexity of a civilization?
Yeah, this is where they really hit the core problem they're tackling. Even with all that existing work, they point out several major limits preventing current systems from reaching that kind of civilizational scale. Okay, first big one. Agents in many of these current systems are not really truly autonomous. They might seem independent to a degree, but often they need a lot of human hand-holding, frequent instructions, or they operate inside really tight constraints.
So they're not fully independent actors making complex choices over long stretches of time on their own.
Not in the way you'd need for, like, emergent societies. And even when they do have some autonomy, their actions and how they interact are often limited by the system's architecture or the simulation world itself.
How so?
Well, it could be things like turn-based execution agents act one after another, not all at once in real time.
Okay.
Or really rigid workflows, where they can only do a very narrow set of predefined things, or even stiff communication rules, where they can only exchange information in very limited, structured ways.
That sounds like trying to build a bustling city where everyone has to wait their turn to speak and can only use government-approved sentences. Very different from messy, real-time human society.
It's a totally different setup, fundamentally. And while the paper does mention that some large-scale simulations exist, they talk about simulations with up to 18,000 personas, which is a huge number.
Wow.
These are often limited in the type of interaction they model. They might simulate how info spreads on a social network or simple connections, but they don't usually involve agents having fully autonomous, complex social conversations and taking physical actions in truly open worlds over long periods.
So you can model maybe who texts whom, but not agents spontaneously deciding, hey, let's form a trading guild.
Yeah.
Or working together to build something complicated in a dynamic virtual world.
Exactly. The paper points this out. Fully autonomous social chat and complex action in open-world real-time settings at the scale of hundreds or thousands of agents. That hasn't really been explored much.
Sure.
Previous big multi-agent experiments usually involved either lots of agents doing simple restricted things or fewer agents doing complex things, but in constrained environments. It's the combination full autonomy, complex interaction, open-world dynamics, and massive scale that's needed for civilizational emergence. And that's the gap. They mentioned the biggest experiments looking at complex autonomous behavior with social interaction were usually capped around like 25 to 50 agents.
25 to 50. Yeah, that's way different from the hundreds or thousands you'd need for really complex society stuff to happen.
Totally different scale.
Okay, so the vision is huge AI societies with emergent structures, collective progress. The current reality is smart individual agents and multi-agent systems that are either small, super constrained, or just lack that true autonomy and complex real-time interaction needed for a civilization. That really paints a clear picture of the gap this research wants to bridge.
Yeah, it perfectly sets the stage for the major technical and behavioral hurdles they knew they had to tackle.
All right, so we get the ambition and the current limits. Now let's really focus on those core obstacles. What makes scaling AI agents up to build something like a civilization so darn hard? The paper breaks it down. What's obstacle number one?
The first big one they identify is that single agents often really struggle to maintain consistent progress over time. Even the smartest LLM agents we have today have this fundamental issue with what the paper calls grounding.
Grounding.
Yeah, basically staying connected to reality, maintaining a consistent, accurate sense of what's real, their own state, the environment state, and their actions and their reasoning, especially over time.
Okay, grounding. Staying tethered to reality. For an AI, what happens when that fails? What does it look like?
Well, when an agent isn't grounded, its internal beliefs, its decisions, they can kind of drift away from what's actually happening around it, or even what it just did. And the results are pretty bad. Agents can get stuck doing the same useless thing over and over, or they start accumulating errors through what we call hallucinations.
Ugh. Hallucinations. We hear about LLMs doing that with text, making stuff up. How does that apply to an agent acting in a world?
It's similar, but maybe more impactful. It means the agent generates an output or maybe reaches a conclusion internally that just isn't true about its current situation.
So it's not just writing fake news, it's genuinely believing things about itself or the world that are false.
Exactly. The paper gives this really simple, clear example. Imagine an agent in a simulated village. You ask it, hey, what are you eating right now? And maybe it's not eating anything at all, but it might still confidently hallucinate and reply, oh, I'm eating a delicious bagel.
Okay, seems like a small mistake. But how does that little hallucination stop it from making real progress?
Because that one wrong piece of info, I just ate a bagel, gets logged into the agent's internal state, its working memory, and it basically poisons everything that comes after.
Yeah.
The agent now believes it ate. So based on that false belief, its planning module might think, okay, cool, I'm full, don't need food right now, I'll go do something else. But in reality, it's still hungry. And eventually, it's going to fail at any goal that requires it to actually be fed within the simulation.
I see. So one tiny error, one false belief just cascades down through the whole decision-making chain and leads to wrong actions or failing to meet its actual needs.
Precisely. The paper emphasizes that even if these grounding errors or hallucinations happen only, say, a small percentage of the time, when you compound that over thousands of interactions, thousands of LLM calls, it can totally stop an agent from making any meaningful long-term progress. They just get stuck in these loops where their internal logic is out of sync with reality. They can't pursue complex, multi-step goals effectively. It's like trying to bake a cake but constantly forgetting if you already added the sugar, you're going to mess it up pretty quickly.
That really makes the problem clear for a single agent. But this whole thing is about many agents. What happens when you throw these potentially ungrounded, hallucinating agents together in a group?
Well, that gets us right to the second major hurdle. Groups of agents struggle because of incoherence and miscommunication. Just like an individual agent's internal mess-ups can make its own behavior fall apart, inconsistencies and bad communication between agents can spread errors through the whole group.
Okay.
If one agent acts on a wrong belief, or, crucially, says one thing but does another, it can totally mislead the other agents. And then the whole group might fall into these useless loops or conflict or just completely fail to work together.
So one agent's lack of grounding or coherence becomes everyone's problem.
Exactly. The paper uses another great example here involving two agents, let's call them Abby and Bob. They need to work together. Abby is built with separate LLM modules for different jobs. Like one decides physical actions, another generates chat. So Bob needs a pickaxe from Abby to go mining. Bob's agent asks Abby's agent for it. Now, Abby's chat module might process this and say, sure thing, on my way with the pickaxe, giving Bob the signal that help is coming.
Okay, sounds good so far.
But at the same time, Abby's action module might independently decide, you know what, exploring that cave looks more interesting right now. Maybe because its internal planner prioritized finding rare stuff over helping Bob at that exact moment.
So Abby said she'd help, but then her body essentially walked off in the other direction.
Precisely. There's a total disconnect between her communication output and her physical action output. So Bob, who trusted her words, might just stand there waiting for a pickaxe that's never coming. Or worse, try to start mining thinking he has the tool. This lack of sync between an agent's different behaviors, talking, acting, maybe even looking, is a huge form of miscommunication at the system level. If that happens all the time, it just destroys any chance of reliable teamwork.
That really highlights this need for the agent to be, internally consistent across all the ways it interacts with the world and other agents. What's the term the paper uses for that quality?
They really stress this concept of coherence. They define coherence as this quality where outputs from an agent's different behavior streams like speech, physical actions, where it's looking, etc., have to be bidirectionally influential and consistent with each other. What it says should match its plans and its actions should match what it communicates.
Coherence. Got it. Making sure all the agent's parts are singing from the same hymn sheet, basically. Why is keeping this coherence so tough, especially when you scale up and have things happening in real time?
It gets incredibly hard because in a dynamic world like a simulation or a robot moving around, agents need to react fast, often with really low latency. And they might have tons of different outputs to coordinate at the same time, moving arms, legs, talking, changing expression.
Yeah, a lot going on.
So coordinating all those outputs, making sure they're all consistent with the agent's current goals, beliefs, ongoing actions, and doing it all concurrently and super fast. That's computationally really, really complex. The paper mentions that, yeah, maybe a very simple agent could achieve coherence by having just one single LOM call decide everything at once. Dialogue, action, the works. But that just doesn't scale up when you have complex agents with many different kinds of outputs happening over time. The different parts kind of need to run somewhat independently to be fast and efficient, but they still desperately need a way to stay coordinated. They even bring up human examples like split brain patients, where the lack of communication between brain hemispheres leads to incoherence, like one hand doing something completely different from the other. It shows how fundamental this coordination problem is.
Wow, that split brain analogy really drives it home. Okay, so individual agents struggle with grounding, groups struggle with coherence and miscommunication. What's the third big roadblock they faced?
The third one's a bit different. It's about measurement. The paper points out there's a major lack of benchmarks for measuring civilizational progress.
What do AI benchmarks usually measure right now?
Well, current benchmarks mostly focus on how well a single agent does on specific tasks, right? Can it search the web well? Can it write code, solve math problems, answer tricky reasoning questions? And there are also benchmarks for multi-agent systems. But like we said, they usually focus on specific interactions in small groups. They measure things like how effectively do they communicate, how good are they at competing, cooperating, or delegating tasks between just a few agents.
So things like those specific named benchmarks, battle agent bench, co-MMA, villager bench testing skills, in pretty limited scenarios.
Exactly. Those are useful tools for certain things. But the paper highlights this huge gap. Those existing metrics just don't capture the kind of complex, large-scale progress that lots of agents make together at the scale of a civilization. How do you even quantify the emergence of institutions? Or the complexity of an economy? Or a cultural evolution? Or governance structures across hundreds or thousands of agents?
Yeah, that sounds like a totally different measurement challenge. Why hadn't people developed those kinds of large-scale civilizational benchmarks before?
Well, according to the paper, it basically comes back to the sheer technical difficulty we've been talking about. Until very recently, it was just technically super hard, maybe impossible, to run simulations with hundreds or thousands of these complex autonomous agents interacting dynamically in one open world for long periods. They point out again, those largest experiments with complex agents interacting socially were maybe 25 to 50 agents. That's just orders of magnitude too small to see or measure processes that look like civilizational development. You can't measure civilizational progress if you can't even simulate a big enough population for it to potentially happen in the first place.
Okay, that really lays it all out. The road to AI civilizations is blocked by these huge mountains. Single agents losing touch with reality, groups falling into incoherent chaos, and just the basic inability until now to even run these systems at the scale needed, which means we don't even have the right yardsticks to measure civilizational progress if it did happen. That's a serious set of challenges.
It definitely is.
Yeah,
And it
okay.
really highlights why just trying to scale up the old multi-agent systems wasn't going to cut it. They needed a completely different approach to how these agents are built and simulated.
So faced with these massive hurdles, grounding problems, incoherence, the simulation scale barrier, the researchers came up with a new architecture to try and solve them. And this is where Piano enters the picture.
Yeah, PNO stands for Parallel Information Aggregation via Neural Orchestration. It's their proposed solution, designed specifically to get past those limitations we just talked about and actually enable simulating these complex, large-scale agent societies. And the name itself kind of hints at its brain-inspired design.
Parallel information aggregation, neural orchestration. Sounds fancy. And you said brain-inspired. How's that work?
So they built it around two core design principles they explicitly say are inspired by how the brain works. The first one is concurrency.
Concurrency, like lots of things happening at the same time.
Exactly. The problem we mentioned is that typical LMM agents are often sequential, single-threaded. They think, then act, one step at a time. And all their thinking processes kind of run at the same speed. But for an agent to handle a complex, fast-moving world and interact smoothly with others, it needs to be able to think slow, do deep reasoning, planning, reflecting, but also be able to act fast, react instantly to sudden dangers or opportunities or social cues. The human brain juggles this all the time, running tons of different processes together at different speeds.
So if an agent is deep in thought, planning its next big project, it still needs to be able to, instantly dodge a falling rock or answer a quick question from another agent.
Exactly that capability gap. Piano tackles this by designing the different agent modules, like modules for cognition, planning, physical actions, they sometimes call it motor, generating speech to all run concurrently, in parallel. They describe these modules as basically stateless functions that are constantly reading from and writing to this shared internal thing called the agent state.
A shared agent state, okay, like a central blackboard or database where all the different parts of the agent can see the latest info and update it.
That's a really good way to put it. It's this central pool holding everything the agent knows or believes its current state, what it sees, its goals, memories, info about other agents, everything. Each concurrent module can tap into and update this shared state independently.
Okay, so the part handling vision might be constantly updating the state with saw tree, while the long-term planning part is reading the state to adjust its strategy, and a quick reaction part is also scanning the state for danger signals.
Yes, all happening at the same time. And this design lets different modules run at different speeds. You can have fast, simple modules using smaller neural nets for quick reflexes or processing immediate senses, running right alongside slower, heavier modules that might use big LLM calls for deep thought or generating long-term goals. It also allows for selective engagement. Like a social awareness module might only ramp up its activity and interact heavily with the state when other agents are actually nearby and talking. It's like the different sections of an orchestra, the modules all playing their part simultaneously, concurrently reading from the same score, the agent state to create the overall music, which is the agent's behavior.
That's where that pianist coordinating notes analogy they used fits perfectly. Different fingers, different notes, different speeds, but all working together. Okay, so concurrency allows for this complex multi-speed processing, but having all that stuff running at once sounds like it would lead straight back to that second problem we talked about, incoherence. How does Piano stop that from happening?
Right, that leads straight to the second core principle, which is all about managing coherence. And they do it via a bottleneck. As you said, if you have all these independent modules running concurrently, trying to generate outputs, controlling movement, talking, changing expression, it's super easy for them to get out of sync and produce conflicting behaviors, like saying one thing while doing another. And this problem gets way worse the more output streams you have. They bring up that biological analogy again, how cutting communication paths in the brain leads to incoherence.
So how does Piano keep all these parallel processes, coherent, singing the same tune?
They introduced this specific central module called the Cognitive Controller, CC. The CC is designed to be the main decision maker for the agent's high-level goals and intentions. It takes a more global view of the agent's state and decides, basically, what the agent should be trying to achieve strategically.
So the CC is like the conductor coordinating the whole orchestra.
Kind of, yeah, but with this crucial mechanism that's key for coherence. The Cognitive Controller pulls information from the whole shared agent state, but it does it through a bottleneck.
A bottleneck. That sounds restrictive. Why would you deliberately limit the info the main decision maker gets?
Yeah, it seems weird, but the paper argues it serves two really important functions. First, it acts like an information filter. It drastically cuts down the amount of raw data the cognitive controller has to deal with at any one moment.
Okay.
This lets the CC, which might be using a powerful but maybe slower LLM for that thinking slow deliberation, focus its computing power only on the most relevant bits of info from the agent state needed to make a high-level decision right now. It stops it getting swamped by the constant flood of updates from all the other modules.
Like giving the conductor a simplified score, highlighting just the important parts instead of the full sheet music for every single violin.
That's a great analogy. It helps the CC focus its deliberate thought. The second reason is that this bottleneck gives the system designers a control point. You can specifically design the bottleneck to prioritize certain kinds of information, getting to the cognitive controller. So, for example, if you want an agent that's really tuned into its social world, you can make sure info from the social awareness module consistently gets through the bottleneck to influence the CC's decisions.
Okay, so control and focus, those are the benefits of the bottleneck. Once the cognitive controller makes its high-level decision, how does that decision make sure all the other parallel modules, like the talking part or the action parts, stay coherent?
Right. So once the CC decides on a high-level goal, like, okay, my main goal now is to find water because I'm thirsty, that decision isn't just kept secret. It gets broadcast back out to many of the other modules. And crucially, it strongly influences or conditions the outputs of modules, like the talking module and the action execution module. So if the CC decided, find water, the talking module is prompted to generate speech that fits that goal, like, man, I'm thirsty, gotta find a river. And the action module is guided to pick actions relevant to that goal, like moving towards water, looking for signs of water. This broadcasting step links the agent's internal decision to its external behaviors, making sure they stay consistent and coherent. They even connect this idea to theories about human consciousness, or maybe a bottleneck decision center broadcasts its state to coordinate the rest of the brain.
That's fascinating. So concurrency lets lots of things happen at once, while a bottlenecked cognitive controller acts as the central strategist, filtering info for focus and then broadcasting its decisions to keep all the outputs aligned and coherent.
Those two principles are really the architectural bedrock. And built on that, the full piano system has 10 distinct concurrent modules, all interacting with that shared agent state and coordinated by the CC. We don't need to list all 10, but besides the cognitive controller, some key ones are the memory module for storing and recalling experiences, the action awareness module for checking if its own actions actually worked, the goal generation module for coming up with objectives, the social awareness module for understanding other agents, the talking module for language, and the skill execution module for turning intentions into actual actions in the world.
Wow, it sounds like a really complex, interconnected system, all designed to let agents be capable on their own, but also socially aware, thinking and acting in parallel while staying internally consistent.
That's definitely the goal. By putting these specific modules together within that concurrent bottlenecked architecture, they're aiming to create agents that show the kind of continuous, coherent, responsive behavior you need to operate in a dynamic, multi-agent world and hopefully scale up to complex societies.
Okay, so the piano architecture is the proposed solution, based on these brain-inspired ideas to tackle grounding, incoherence, scale. But, the proof is in the pudding. Does it actually work? The paper then talks about their initial tests, showing if the architecture works at the individual and small group level first. Where did they decide to test this thing?
They chose Minecraft.
Minecraft.
Ow.
The blocky sandbox game.
Yep. And it was a pretty smart choice for this kind of research, actually. Minecraft gives you this huge, open-ended world. Agents can explore, gather stuff, craft tools, build things, interact with the environment using complex actions, and talk to each other using natural language.
Right.
And importantly for their goals, Minecraft as a platform is really scalable. You can potentially host large numbers of agents all interacting at the same time in one shared world.
Makes sense. It's complex enough for interesting behavior, but still controllable for experiments. So how did they first test if it worked just for a single agent?
For individual progress, they used item acquisition, basically. How many different kinds of items an agent could collect within Minecraft as their main measurement?
Item acquisition. Why collecting items? How does that show how sophisticated an agent is?
Because, as they explain, making progress in Minecraft often means working through this really complex dependency tree of items and actions.
Ah, okay.
To get advanced stuff, you need simpler stuff first, which needs specific tools or materials, which need other tools. Like, to get diamonds, you need a diamond pickaxe made from diamonds and sticks. But to mine the diamonds in the first place, you need an iron pickaxe. To make that, you need iron ingots from a furnace. To build a furnace, you need cobblestone, which needs any pickaxe, even a basic wooden one.
Right, right. It's a whole chain reaction.
Exactly. So getting advanced items forces the agent to plan, sequence lots of sub-goals, craft things, use tools right, and keep at it over time. It's a really good proxy for complex problem solving and sticking with a goal. They wanted to see if agents could get a good chunk of the nearly 100 unique items in the game.
That's a clever benchmark. It really captures deep progress, not just simple button mashing. So what did they find? Could single agents using piano actually make progress?
Yeah, they did. In experiments where they put 25 agents far apart in a world specifically to minimize social stuff and focus on individual gathering with the goal of just getting items, agents using the full piano architecture showed pretty significant progress right off the bat. On average, they picked up about 17 unique items in just 30 minutes.
Okay.
And when they ran logger tests, like 49 agents over 4 hours, the total number of unique items collected by all agents in that world kind of leveled off around 320 items.
17 items in 30 minutes for one agent, topping out around 320 collectively in 4 hours. Is that good? How does that compare?
Well, they do note there was a lot of variation depending on where an agent happened to spawn. Some started in really resource-poor areas and didn't get much. But the top-performing agents managed to grab between 30 and 40 items in that first 30 minutes.
Ah, okay, so the best ones did quite well.
Yeah, and the researchers state that this rate for the top agents is actually comparable to a human player who knows Minecraft reasonably well. So it shows the agents weren't just wandering randomly. They could make complex plans, deal with challenges, make real individual progress without constantly messing up or getting stuck, which directly addresses that grounding problem we talked about.
And were there specific parts of the piano architecture that seems really important for this?
They specifically call out the action awareness module. Remember, that's the part that lets the agent compare what it thought would happen when it acted versus what actually happened in the world.
Right, the reality check module.
Exactly. They did an ablation study, they ran the experiment again, but turned off that module. And they found agents without action awareness collected noticeably fewer items. This suggests that the agent's ability to kind of self-monitor and correct its behavior based on seeing the real results of its actions was super important for learning and making steady progress.
So basically, learning from mistakes or checking if things worked was critical. Did the underlying LLM matter? The brain power behind it all?
Oh, absolutely. The paper's really clear on this. They say getting this level of robust progress was only possible using the best model they had access to then, which was GPT-4o. When they tried using older LLMs as the base for piano, they just didn't get the same level of performance or sustained progress. So it underlines that while the architecture is vital, you also need that raw power from the underlying model. They also briefly compare it to other Minecraft agents like Voyager, noting some differences in how performance was measured and that Voyager had some extra help like an auto-curriculum, making direct comparisons a bit tricky.
Okay, so piano architecture, especially things like action awareness, plus a powerful LLM like GPT-4o, lets individual agents make real human-like progress in a complex world. That's a solid start. But the big goal is multi-agent systems, societies. How do they show progress at the group level?
Right, so for multi-agent stuff, the focus shifts to collaboration, interaction, how well agents function in a group. And that requires understanding others, their presence, their intentions. It connects to that idea of theory of mind, reasoning about others' mental states. They call it bidirectional awareness.
Yeah.
Being aware of yourself and others.
Okay, and how did they test that social side?
They started small, with experiments in small groups to see if they could establish basic social understanding. In one test, they had 3 characters interacting with one agent named Leela. They found that when Leela had her social awareness module turned on, the part designed to process info about other agents, she could accurately figure out the changing feelings of the character she was talking to just based on their speech.
Wow.
But when they did the ablation, turned off her social awareness module, she completely lost that ability to track their emotions or attitudes.
So the agent could tell if someone was happy, mad, or neutral towards it just from the chat.
Yeah, basically. They showed it could process the dialogue and correctly infer the sentiment, and that this ability depended specifically on that social awareness module. Then, they tested if agents actually used this social info to change their actions. They set up another small group test with a chef agent who had limited food to give out to 4 other agents. And these 4 agents were preset to have different feelings towards the chef. Some liked him, some didn't.
What did the chef do with the food? Give it out fairly?
Nope. The chef agent didn't just distribute it randomly or evenly. It actually selectively gave food to the characters that its social awareness module figured out liked him the most, the ones showing positive sentiment towards him.
Whoa!
So that showed the agents weren't just passively reading the room, they were actively using that social understanding to make strategic choices, like who gets resources. Within a group, it's a form of social intelligence.
That's pretty sophisticated, picking up on social vibes and using them to influence actions like sharing food. How did these basic social skills hold up when they scaled up to bigger groups?
That's when they moved on to simulating societies with 50 agents. They put these 50 agents into randomly generated Minecraft worlds. Each agent got a distinct personality profile, like introverted, extroverted, agreeable, disagreeable, stuff like that. And they were just let loose to act and interact freely with each other and the environment for 4 hours, which was like 12 in-game days.
50 agents loose in Minecraft for 12 game days? What happened?
They found that those basic social dynamics they saw in small groups mostly held up. Agents could still figure out who liked whom based on interactions, and they actually got better at it over time as they interacted more. They learned about each other. And again, turning off the social modules broke this relationship building ability.
Okay, so the basic scale. Did anything new or, I don't know, unexpected pop up only at that 50 agent scale?
Yes. And this is where it gets really interesting for emergent behavior. At that 50 agent scale, they started seeing social structures emerge that weren't programmed in. They just arose from the interactions influenced by those personality traits.
Like what?
For instance, they found that agents with personalities defined as more introverted tended to have fewer incoming social connections, fewer other agents starting chats with them or liking them compared to the extroverted agents who generally had more social ties.
Wow, seriously. So even in this simulated AI society, personality affected the social network. Introvert AIs were less popular.
That's what their interaction data showed. Yeah,
Mm.
a clear link between personality and social network position. They also saw the emergence of non-reciprocal relationships, like Agent A might develop a strong positive feeling towards Agent B based on their chats, but Agent B might not feel the same way back.
Huh. Unrequited AI love.
Sort of. It reflects that messy, unbalanced nature of real human relationships, right? Not always mutual.
That's amazing. Emergent personality-driven social networks and even unreciprocated social feelings just popping up spontaneously in 50 AIs. It really shows that with the right architecture and enough scale, these basic social skills can lead to complex, self-organizing group dynamics that start to look a bit like human societies.
Yeah, these initial tests show that Piano enables both solid individual progress and scalable social understanding and interaction. It proved the agents could function as individuals and as interacting members of a group, which is crucial groundwork for looking at higher-level organization.
Okay, so we've seen individual agents make real progress, groups showing these emergent social dynamics thanks to Piano. This really sets the table for looking at something closer to the paper's big goal, seeing actual signs of civilizational progress. And the first marker they really dig into is specialization.
Right, specialization. It's seen as like a cornerstone of how civilizations develop. In human history, the division of labor people specializing as farmers, blacksmiths, builders, rulers, whatever, was totally critical.
Yeah, huge driver.
It led to more efficiency, new technologies, complex institutions, economies. It's a key sign that a society is moving beyond just basic survival towards organized complexity.
So the researchers basically wanted to see if their AI agents, without being told you're a farmer, would just spontaneously start doing different jobs within a bigger group.
Exactly. But they set really specific, tough criteria for what counts as emergent specialization, based on how it works for humans. First, agents have to show autonomy in choosing and maybe changing roles. It can't be assigned by the researchers.
Okay.
Second, it has to genuinely emerge from their interactions, experiences, the environment, not be explicitly directed or forced. And third, their actual behaviors have to match their chosen specialization. If an agent seems to be a miner, it better be spending a lot of time actually mining.
Those are high bars to clear autonomously. How did they set up the experiment to test for it?
They ran a simulation with 30 agents inside a Minecraft village. All agents started with the same basic goal: survive and help the village become more efficient and progressive. They had the same initial personalities and some basic knowledge, like where the farms were, the mine entrance, the town hall.
So no job titles, no instructions like you're on farm duty, just a shared goal and knowing where things are.
Precisely. The whole idea was to create a situation where specializing could be helpful for the group goal, and then just see if it happened on its own. The process involved agents constantly trying to figure out what other agents seemed to be doing their goals, their skills, based on watching and interacting. And based on these profiles of others, their own personality, and what the village seemed to need, agents would generate these social goals for themselves every few seconds.
Social goals. Like, Agent Bob looks like he's struggling with that building, maybe I should help, or looks like we're low on food, I should probably focus on farming for a bit.
Exactly, those kinds of thoughts. Inferences and self-directed aims driven by their social awareness and the environment. These social goals, mixed with their other internal goals and observations, then fed into their high-level intentions, which Piano translated into actual actions in Minecraft.
Okay, so what happened? In this 30-agent village simulation, did specialization actually emerge?
Yes, they found really strong evidence that the agents did autonomously sort themselves out and specialized into this diverse set of roles that look a lot like different parts of a developing civilization.
Really? Like what kind of roles?
Oh, the paper shows data for roles like farmers, miners, engineers, guards, explorers, blacksmiths, traders, a whole range. The figures in the paper actually show the breakdown of how many agents took on which role over time.
That's pretty wild, a spontaneous division of labor into complex roles. Were the roles stable? Or did agents just flip-flop randomly?
That was another key finding supporting genuine specialization. While the mix of roles varied across agents, for any individual agent that specialized, that role tended to be pretty persistent over the 4-hour simulation. They didn't just randomly try stuff. They seemed to settle into a role and stick with it, suggesting a stable internal state linked to that specialization.
Was that social capability we talked about, the social awareness module, understanding others, important for this specialization to happen?
Absolutely critical. They did another ablation study,
Mm-hmm.
ran the village simulation again, but this time with the agent's social module switched off. And the results were dramatic. Agents without social awareness failed to specialize.
Wow.
Their behaviors stayed much more similar, more homogeneous, and they didn't settle into stable roles over time. The paper shows figures comparing the two conditions, and it's a stark difference. This is strong evidence that the ability to perceive, interpret, and react to what other agents are doing, basically, understanding the social context and where they might fit in or contribute, was essential for this division of labor to emerge.
So it wasn't enough for them to just do their own thing. They needed to understand the group situation and what others were doing to figure out their own niche and specialize.
Precisely. Understanding the social landscape seems to be what drove them to find these roles that benefited the group. They also tested if the overall goal of the village could influence the types of roles that emerged. They set up villages with either a collective martial goal focused on defense, tech, or an artistic goal focused on culture, art.
And did it make a difference?
Yeah, they observed that the high-level goal did lead to different role distributions. Like, roles related to fighting or scouting only really showed up in the martial villages, while roles like curator or collector popped up in the artistic ones. So it suggests the specialization isn't rigid. It adapts to the group's collective aims and environment.
That shows a really fascinating level of emergent organization and flexibility. But did this self-assigned role actually translate into different actions? Were the farmers really farming?
Yes, they dug into the specific low-level actions agents performed and connected them back to their identified roles. And the data strongly showed that the emergent roles massively dictated what actions agents took.
Okay.
They give specific examples. Agents identified as artists spent a lot of time picking flowers used for dyes. Farmers focused on gathering seeds, tilling land. Guards and builders spent time crafting and placing fences for defense.
And were those actions mostly exclusive to that role?
Largely, yeah. The paper notes that most specific actions they looked at were predominantly done by agents in just one or maybe a couple of related roles, and weren't common for agents in other specializations. It's really compelling evidence that the agents effectively translated their high-level, chosen roles into consistent, appropriate, low-level behaviors in the world. Their specialization wasn't just a label. It really shaped what they did.
That's a powerful demonstration of emergent organization. It feels like a solid first step towards that institutional development part of their civilization definition. Shows that large groups of these agents, with the right setup, can move beyond just chaos towards organized role-based behavior, a division of labor.
Yeah, it's a critical piece of evidence showing that the piano architecture can actually facilitate the emergence of complex societal structures, kind of from the bottom up.
Wow. This deep dive into the foundations of AI civilizations has definitely taken us on quite a ride. We kicked off with that really ambitious vision, building systems of AI agents that can autonomously collaborate, self-organize on a massive scale, setting this idea of civilizational progress as a new ultimate goal for AI.
Then we really laid out those huge technical and behavioral roadblocks, how individual agents struggle to stay grounded and avoid errors, the immense challenge of coordinating lots of concurrent agents coherently without miscommunication, and just the sheer difficulty of simulating these systems at scale, which meant we didn't even have the right benchmarks.
And we explored the paper's proposed solution, that piano architecture, with its brain-inspired principles, concurrency, letting agents think and act at different speeds simultaneously,
Right, across different modules.
and coherence, managed through that bottlenecked cognitive controller, making sure the high-level decisions keep all the parallel parts working together.
We also went through their initial demos, showing it actually works at basic levels. Significant individual progress in Minecraft, helped by things like action awareness and powerful models like GPT-4o. We saw how they proved social capability in small groups, leading to those really fascinating emergent social dynamics when they scaled up to 50 agents.
And crucially, we dug into their first big civilizational benchmark, specialization, seeing how 30 agents could spontaneously organize into diverse, stable roles like farmers and miners, how social awareness was absolutely key for that division of labor, and how those roles directly shape their actions.
Yeah, this research really feels like a foundational step. They're not saying we built a civilization, not yet. But they've provided an architecture and some initial real evidence showing that building and evaluating AI agent systems at the scale needed for complex societies might actually be within reach now.
It really opens up completely new ways to study emergent behavior in artificial societies and maybe rethink how complex AI systems might organize themselves down the line.
And, what we've talked about today, that's really just the beginning of what they found. The paper goes into even more fascinating aspects of civilizational progress they observed.
That's right. In our next deep dive, we're going to explore how these agents started dealing with collective rules, stuff that looks uncannily like laws and even voting, and we'll uncover the really surprising emergence and spread of culture, including memes, and get this, organized religion within their simulations.
Yeah, the idea of AI agents spontaneously creating culture and belief systems. That's truly remarkable stuff. Definitely something you won't want to miss.
Indeed. Which kind of leaves us with this thought to chew on, building on today's discussion. If AI agents, just starting from simple goals and interactions, can autonomously form roles, specialize, start organizing themselves in simulations, what does that tell us about the potential complexity of AI societies in the future, and maybe how they might eventually interact or integrate with our own?
Or looking ahead, what other completely unexpected complex behaviors might pop up as these artificial civilizations get bigger and evolve even further?
Definitely food for thought. Thanks for joining us for this deep dive. We'll catch you next time as we continue unpacking this groundbreaking research into the world of AI civilizations.